Consistent linear systems. In this video, we will introduce augmented matrices, fundamental questions of existence and uniqueness of solutions, and row equivalents. By the end of watching this video, and maybe after solving a few worksheet problems or discussing these concepts with a friend, you should be comfortable expressing a set of linear equations as an augmented matrix and characterizing a linear system in terms of the number of solutions and whether the system is consistent or inconsistent. So first, augmented matrices. It is redundant to write the variables x1, x2, ... however many we need, again and again. So we rewrite our systems using matrices. For example, this is a linear system with two equations and three unknowns. We can express this system as with an augmented matrix. The vertical line, not strictly necessary, but it reminds us that the first three columns give us the coefficients to the variables. The last column gives us the numbers on the right-hand side, 0 and 7 in this case. Row operations can be applied to augmented matrices as though they were just the coefficients in a linear system, because they are. And so this gives us a more convenient way of expressing a linear system. We say that a linear system is consistent if it has at least one solution. There could be more than one, but if there's at least one, the system is consistent. Two matrices are row equivalent if there is a sequence of row operations that transforms one matrix into the other. Going back to the augmented matrix representation, well, if two matrices, augmented matrices, corresponding to linear systems, are row equivalent, then, well, there's a sequence of row operations that take one to the other, and the systems will have the same solution set. So, let's go through a quick example. Suppose I have these three matrices, A, B, and C. And I'm not saying whether or not they are augmented matrices or just matrices, but are matrices A and B row equivalent? Well, yes. I mean, if I take row 2, let's see if I can write this a little bit better. A is 1, 1, 0, 1, and I take the second row, row 2, and I subtract the first row from the second row, so I go R1 minus R2, put that in the first row, I get 1 minus 0 is 1, 1 minus 1 is 0, 0, 1. So there's a sequence of row operations, in this case just one row operation, that takes me from A to B. So A and B are row equivalent, so yes. Are A and C row equivalent? No. I would need to multiply the second row of A by 0, and multiplying a row by 0 is not a row operation. Remember, row operations, I can multiply a row by a non-zero number. I can add a multiple of a row to another row, and I can swap rows. And in no way could I multiply a row by 0. So A and C are not row equivalent. So, I mean, what does that have to do with linear systems? Well, question 2. Do these augmented matrices correspond to consistent systems? So you'll recognize the first augmented matrix involves matrix A, and the second involves matrix C. Well, first of all, this first augmented matrix does have a solution, and that solution is, well, it looks like x2 has to be 1, and I guess x1 is 0. So the solution is the point 0, 1. This is not a consistent linear system. So notice how the that third row gives us 0x1 plus 0x2 is equal to 1. The second row gives us 0x1 plus 0x2 is equal to 1, which is 0 cannot be equal to 1, so we have an inconsistent system. There's no x1 and x2 that will satisfy both equations. So notice how the solution sets are different, even though I've used A and C here and found that they have different solution sets. Okay, so that's all I wanted to really say. I just wanted to introduce augmented matrices, row equivalents, and what a consistent linear system is. And this allows us to explore some fundamental questions that we revisit many times throughout our course. Does a given linear system have a solution? In other words, is it consistent? And if it is consistent, is the solution unique?